El Capitan is the most powerful supercomputer on Earth. To solve the universe's most complex mathematical problems, it requires about 10 septillion years. But Google's new Willow chip reached that same solution in 5 minutes. This gap exists because of the language classical computers speak. They rely on binary bits, rigid on and off switches. Nature, however, operates through the fluid behavior of subatomic particles that overlap and interact in ways a series of ones and zeros cannot accurately represent. For decades, we tried to solve this by scaling up the hardware. We moved from room-sized mainframes packed with thousands of hot, fragile vacuum cubes to the microscopic silicon chips of today. But we have reached the end of that path. Silicon transistors have been shrunk down to the size of individual atoms, hitting a hard physical limit where electricity can no longer be controlled by classical means. Breaking this barrier requires a complete departure from the physics that governed the last century of technology. We have to move past the binary bit entirely. That departure begins with the qubit. While a standard bit is like a coin resting on a table, fixed as either heads or tails, a qubit exists in superposition. It's represented by a coin spinning in the air, acting as both states simultaneously until the moment it's measured. In a complex maze, a classical computer must test every path one by one. It travels down a corridor, hits a dead end, retracts, and starts over. A 100-qubit processor utilizes superposition to flood that same maze, exploring 1.26 nonillion paths simultaneously. Quantum computers utilize the interference of probability waves. By mathematically suppressing the noise of incorrect paths, the system allows the correct solution to emerge almost instantly. This immense processing potential is fatally fragile. The state of the wave is highly sensitive to its environment, a phenomenon known as quantum decoherence. If a qubit interacts with even a single stray molecule or a microscopic spike in heat, the superposition shatters. The quantum information is lost, and the system collapses back into classical noise. To prevent this, engineers house the chips inside dilution refrigerators. These massive structures use liquid helium to drop the temperature to absolute zero, creating the coldest and most isolated environment possible. Even in these extreme conditions, the fragility persists. In the Willow chip, a qubit can only hold its data for about 100 microseconds before it decays. To run a 5-minute calculation on a system that fails every fraction of a millisecond, scientists developed quantum error correction. This works like a relay race. Before a qubit can collapse, its information is transferred to a fresh group of helper qubits. This cycle repeats thousands of times per second, keeping the data alive and moving forward. This turns quantum computing into a high-stakes engineering sprint. Every complex calculation is a race to reach the solution before the environment inevitably pulls the hardware back into classical reality. Quantum machines are designed to simulate the systems that occur at the subatomic level. They operate using the same laws that govern the physical world. In 1981, Richard Feynman observed that because nature is quantum mechanical at its core, simulating it requires a machine built on those exact principles. This enables us to model protein folding with atomic precision. We can see exactly how subatomic forces shape a molecule, tracing interactions that are too complex for classical math to approximate. By modeling these interactions with perfect fidelity, we remove the mathematical guesswork that has historically limited our understanding of biology. This precision allows researchers to see how a drug molecule binds to a specific virus with atomic accuracy. It replaces years of laboratory trial and error with direct simulation, accelerating the development of treatments for currently incurable conditions. By identifying the specific subatomic mechanics that cause cellular decay, we gain the data necessary to intervene in the aging process. This puts the goal of extending the human lifespan to 150 or 200 years within the realm of measurable science. These speeds apply to astronomical data as well. We can analyze the light passing through the atmospheres of billions of exoplanets simultaneously, searching for the exact biosignatures that indicate life on other worlds. We have built a machine capable of predicting nature's most complex outcomes in seconds. If we ask it to solve the mysteries we currently consider impossible, we have to be prepared for what it might reveal.